Dear students, today we'll see some MCQs on operational amplifier op-amps in the topic of analog electronic circuits. So here we will see a few multiple choice questions on operational amplifiers and their applications. So let's start with the third part of analog electronic circuits, and the first question of the third part is question number 41, and in this question it is asked that in ideal differential amplifier, if same signal is given to both inputs, then output will be what? Okay, so if you see an ideal differential amplifier, so we will see a differential amplifier, say we have a symbol of differential amplifier like this. So the amplifier will be having two inputs, input 1 and input 2, and there will be one output. Okay, so this is your differential amplifier. Now here, this input 1, this is V in 1 and this is V in 2. Okay. Now the output of a differential amplifier will be the algebraic difference between the two inputs. So it will be V in 1 minus V in 2. Okay, so multiplied by some gain factor. Now here, this will be your output. Now when both the inputs are same, now if both the inputs are connected to the same value, same input is connected at both the input point, then the output will be difference of the same voltages, because input 1 terminal also is having same input signal and terminal 2 is also having the same input signal. So here the difference between the two will be 0. So anything multiplied by 0, gain factor multiplied by 0, that shows that the output has to be 0. So here the option 4, that is 0, will be the right answer. Then the output will be 0. So here in explanation, we can also remember this. In an ideal amplifier, the output V out is the algebraic difference between the two inputs. And when both the inputs are same, the output will be 0. So here you can see option D, 0, is the right answer for this question. Then we'll go to the next question, question number 42. A differential amplifier is capable of amplifying. The options are DC input signal only, AC input signal only, AC and DC input signal, none of the mentioned. Okay. Now, when we remember about differential amplifier, okay, whatever a coupling we use between two stages, that coupling will be a direct coupling. There is no component used while you're going to connect one stage to another stage. And because of direct coupling, we don't have to use any capacitor or anything. It is a direct coupling. So there is no chance that any DC is blocked or any AC is blocked. Okay, so AC and DC both can be passed. So low frequencies also can be passed. Okay, so if there is a capacitor, we say it can pass AC and block DC. So here in this case, because it is a direct coupling, there is no capacitor, it is a direct connection. So there is no chance of blocking any low frequency or DC. Okay, so that is why a differential amplifier can amplify both types of inputs, whether the input is AC or DC, it can amplify both types of input. So here the option C will be the right answer. AC and DC input signals. A differential amplifier is capable of amplifying AC and DC input signals. So option C will be the right answer here. Okay. So for this, if you see the explanation, so a direct connection between stages remove the lower cutoff frequency imposed by coupling capacitor. That means if there is a coupling capacitor, it will pass AC and it will block DC. So that is gone now because you don't have any coupling capacitor. It is a direct connection. Therefore, this can pass AC and DC both. So both can be amplified. Both AC and DC signal can be amplified by this differential amplifier. So here you can see a differential amplifier is capable of amplifying. Option C is the right answer. AC and DC input signal. Then we'll go to the 43rd question. If output is measured between two collectors of transistors, okay, output is measured between two collectors of transistors, then the differential amplifier with two input signal is said to be configured as what? So what that differential amplifier will be called? Now the options are it will be called as dual input balanced output, or it will be called as dual input unbalanced output, or it will be called as single input balanced output, or it will be called as dual input unbalanced output. Okay, now one thing we can see from the question is there are two input signals. So it is dual input. Okay. So the output is measured between two collectors of the transistor. So if you remember this circuit where you have a transistor where the collectors of the transistors are coupled and emitters also are coupled. So this is the emitter of the transistors. This is joined and the collector of the transistors also are joined. Okay. So if you remember this circuit, so here you can see you can have a VCC supply, and at the base you can give the inputs for both the transistor, and here you can have this emitter connection. So this is emitter base collector. This is emitter base collector. Okay. Now input 1 is given here. So in the question it is said that it has two inputs. So both these inputs are given. V in 1 and V in 2, both the inputs are given. So it is dual input. So we have dual input in 3 of the answers, and there is output taken between collectors of transistors. So output is taken here. So here if you see the circuit, and these are the collectors. Okay, so here you can see here the output is taken. See, this is the collector, and so there is a single output taken. So single output taken is called as balanced output between the two collectors. Okay, so it is a balanced output. And there are two inputs, so it is a dual input. So dual input balanced output will be the right answer here. So option A, that is dual input balanced output, will be the correct answer for this. So when two input signals are applied to the base of transistor, it is said to be dual input. When both collectors are at same DC potential with respect to ground, then it is said to be balanced output. This is the concept which is very important, and based on this only we can have four types of differential transformer, where you can have a single input unbalanced output, you can have single input balanced output, you can have dual input balanced output, you can have dual input unbalanced output. So here the answer is option A, dual input balanced out. Then we'll go to the next question, question number 44. Which of the following electrical characteristics is not exhibited by an ideal op-amp? Now, ideal op-amp characteristics you can remember. Now, ideal op-amp are characteristics were what? So, ideal op-amp we saw that it was having infinite voltage gain, it was having infinite input impedance, it was having infinite bandwidth. Okay, it was having infinite slew rate, it was having infinite common mode rejection. Okay, so all these were there, but the output resistance, whatever was there, it was not infinite, it was low. So it was low output resistance or zero output resistance in case of ideal case, and that is why it was able to be interfaced with any other devices. So that zero output resistance, that is a low output resistance. So here in these options, we are having infinite voltage gain, which is the correct characteristics. We are having infinite bandwidth, which is the correct characteristics. Option C is infinite output resistance, which is wrong. So option C is not the characteristics of an ideal op-amp, because ideal op-amp has or low output resistance or zero output resistance. Okay, so here option C will be the answer. So here explanation, you can remember that an ideal op-amp exhibits zero output resistance so that output can drive an infinite number of other devices. This is very important. That is why we always, in an ideal case, we always expect that the output resistance or output impedance is low, and similarly the input impedance or input resistance should be high. Then that device becomes an ideal device to drive or to connect any of the other stages. So here you can see the answer. Which of the following electrical characteristics is not exhibited by an ideal op-amp? Then the answer is option C, infinite output resistance. Infinite output resistance is the not the characteristics of an ideal op-amp, because ideal op-amp has low output resistance or zero output resistance. Then we'll go to the next question, question number 45. An ideal op-amp requires infinite bandwidth because options are: option A, signals can be amplified without attenuation. Option B, output common mode noise voltage is zero. Option C, output voltage occurs simultaneously with input voltage changes. Option D, output can drive infinite number of devices. Now here, an ideal op-amp requires infinite bandwidth. It is a characteristics of op-amp that it is having infinite bandwidth. Now, what is the bandwidth? Bandwidth is the useful range of frequency which has been amplified by a particular amplifier. Okay, so that useful range of frequency. Now, if that useful range of frequency is infinite, that means it is from 0 to infinity. That means it can amplify all types of signals, whether it is a lower frequency signals or higher frequency signals. It can amplify all signals without any loss or attenuation. That means here the option A will be the right answer. Signals can be amplified without attenuation, that is without loss, without any deterioration. So explanation you can see here, an ideal op-amp has infinite bandwidth. Therefore, any frequency signal from 0 to infinity hertz can be amplified without attenuation, without any loss. So here you can see the option A is the answer. An ideal op-amp requires infinite bandwidth because signals can be amplified without attenuation. Then we'll go to the next question, question of 46. Find the output voltage of an ideal op-amp if V1 and V2 are the two input voltages. Okay, V1 and V2 are the two input voltages. So here the options are V0 is equal to V1 minus V2. V0 is equal to gain, that is A multiplied by V1 minus V2. V0 is equal to gain multiplied by V1 plus V2. And V0 is equal to V1 into V2. Okay. Now we know that whenever we have an op-amp, in op-amp we have two inputs, input 1 and input 2. So this will be input of inverting terminal. This will be the input of non-inverting terminal, and we have one output. Okay, so here V1 and V2, if you apply here, so say that this is V1 and this is V2. If you apply here, the output will be the difference, algebraic difference between the two inputs, V1 minus V2 multiplied by the gain factor of op-amp. Okay, so how many times you want to amplify the difference between the two? That will be the output of an op-amp. Okay, so here if you see the options, now in this options you can see that the second option, that is option B, is the right answer, where it says that the gain factor, that is A, multiplied by the algebraic difference between the two inputs V1 minus V2, and that is the right answer here. So here in the explanation, you can remember the output voltage of an ideal op-amp is the product of gain and algebraic difference between the two input voltages. So here you can see option B is the right answer. V0 is equal to gain multiplied by algebraic difference of the two input voltages. Then we'll go to the next question, question of 47. Find the input voltage of an ideal op-amp. Okay, find the input voltage of an ideal op-amp. It's one of the inputs and output voltages are 2 volt and 12 volt, and gain is 3 volt. Okay, so these are the data given here. So it's one of the input voltage. Okay, so we will see that one of the input voltage is V1. It is given as 2 volt, and the gain is given as 3 or 3 times. Okay, and the output voltage V out is given as 12 volt. Okay, now here we know that the output voltage is equal to gain multiplied by the difference between the two input voltages. Okay, and we have to find out the input voltage here. So here we are having V0, we are having gain, we are having one of the input voltage. We have to find out what is V2, another input voltage. Okay, so here if you substitute the numerical values here, output voltage is 12 volt, then this is equal to gain is 3, V1 is 2 minus V2 we don't know. Okay, so it is 12 is equal to 3 into 2 is 6 minus 3V2. So 12 minus 6 is equal to minus 3V2. So it is 6 is equal to minus 3V2. Okay, then V2 is equal to minus 6 upon 3, that is equal to minus 2. So minus 2 volt will be the value of the input voltage. So the other input voltage should be minus 2, because here you can see if one input voltage is 2 and the other input voltage is minus 2, if you cross check it, if one input voltage is 2 and other is minus 2, so minus of minus 2, this multiplied by the gain, okay, 3 times the gain, that means 3 into 2 plus 2, so 3 into 4, so the output will be 12. So that is right. output is given as 12 volts, so we have cross-checked it. So the other input should be -2 here. So here the option D will be the right answer, -2 volts. So here you can see the explanation. The output voltage V0 is equal to gain multiplied by V in 1 minus V in 2, that is equal to 12 volt is equal to 3 into 2 minus V in 2. V in 2 is equal to -2 volt as we have seen. So here the fourth option, that is the D option, -2 volt is the right answer. Then we will go to the next question, question number 48. Which factor determines the output voltage of an op-amp? Which factor determines the output voltage of an op-amp? Option A is positive saturation. Option B is negative saturation. Option C is both positive and negative saturation voltage. And option D is supply voltage. Okay. Now, which factor is going to determine the output voltage of an op-amp? So here, if you see the explanation for this, okay, both positive and negative saturation voltages are the factor which will determine the output voltage of an op-amp. Now, if you want to remember this explanation, then the explanation can be given as output voltage is proportional to the input voltage only until it reaches the saturation voltage. The output cannot exceed the positive and negative saturation voltage. These saturation voltages are specified by an output voltage swing rating of the op-amp for given values of supply voltages. So here, both the positive and negative saturation voltages will be the option answer. That is the answer C. Option C will be the answer here. So here you can see both positive and negative saturation voltages will determine the output voltage of an op-amp. Then we'll go to question number 49. Op-amp performs dash operations. Now in our applications, we have seen summing amplifiers, we have seen subtractor, okay. So all those arithmetic operations we have seen. We have also seen some logical operations, okay. So here if you see the options, arithmetic operations are performed by op-amp. Logical operations are also performed by op-amp. Alphanumeric are not performed by op-amp. Okay. So here the C will be the right answer. Both A and B, that is arithmetic and logical options, that is arithmetic and logical operations can be performed by op-amp. So option D, both A and B will be the right answer. So both A and B is the right answer here. Then we'll go to the next question, question number 50. The output of a Smith trigger is what? Options are pulse waveform, sawtooth waveform, sinusoidal waveform, and triangular waveform. So if you remember the circuit of Smith trigger, so if you remember the circuit of Smith trigger and its waveforms, so here the waveforms look like, say, if you give a input waveform as a sine wave. So if the input waveform is like a sine wave, then there you will be having two reference points. Say if this is a zero line, then you'll be having two reference points. One will be called as upper threshold voltage, and the second one downward will be called as lower threshold voltage. And whenever the threshold voltage is crossed over by the input, then the output will change its state. That means here, if you see, the output is going to change its state here, it is going to change its state here, and it is going to change its state here. Now here, if you see, initially, it will be, say if you are going to start from here, initially, you can show that it is on the higher side, that is a positive saturation level, and whenever you cross this, you go to negative saturation level. Again here you come, you go to positive saturation level. Again you come here, you go to negative saturation level, and this goes on. Now this type of output for Smith trigger looks like a square wave, or it is a pulse waveform. So you can call it as option A, pulse waveform, because it is not sawtooth, it is not sinusoidal, it is not triangular, it is a pulse waveform. So here the option A will be the right answer, pulse waveform. The output of a Smith trigger is a pulse waveform. Now here question number 51, the below circuit is known as what? Okay, now here if you see a circuit like this, now this circuit where R is there in series with the input, and C, capacitor C is acting as a feedback. R is with the input voltage, R is in series with the input voltage, and component C is acting as a feedback component. So in this case, we remember that it acts as an integrator circuit. It acts as an integrator circuit. So here whenever a resistance in series with the input and capacitor acts as a feedback between the output and the input. So this combination is an integrator combination. So this circuit acts as an integrator. So here the option will be an integrator. Then we'll go to the same type of question, question number 52. The below circuit is known as what? Now here the position of R and C are exchanged. So here with the input, in series with the input, we have capacitor and there is a feedback resistor. Now this is going to act as differentiator. So here the option will be option B, or differentiator circuit. So here you can see the option B is the answer here, or differentiator circuit. Then we'll go to question number 53. A square wave input is applied to this amplifier shown below. The output voltage is most likely to be. The options are square wave itself, triangular wave, sine wave, or no output. Now we know that the circuit shown above is an integrator circuit. And whenever square wave is applied to an integrator, we know that the output will be a triangular wave. Okay. So whenever a square wave is applied to an integrator, the output will be a triangular wave. So here the option will be a triangular. Then we'll go to question number 54. Depending on the value of input and reference voltage, a comparator can be named as what? Okay. So here, whenever we have a concept of comparator, comparator is a circuit which is going to compare two inputs. Okay. So one will be the input and the other will be the reference voltage. So whenever the input is going to cross the reference voltage, the output is going to change its state. That means it is going to check the level, voltage level. Okay. Therefore, a comparator can also be named as a voltage level detector. So here option D will be the right answer, voltage level detector. So if you see the explanation, a comparator is sometimes called as voltage level detector because for a desired value of reference voltage, the voltage level of the input can be detected. So here you can see the answer for question of 54, that is comparator is also called as voltage level detector. Then we'll go to the next question, question number 55. Zero crossing detector is also called as what? Okay, so the options, the answers here are square to sine wave generator, sine to square wave generator, sine to triangular wave generator, and all of them mentioned. Okay, now what is this zero crossing detector? And if you see the waveforms of zero crossing detector, say if this is one input, okay, so it is basically a comparator where the input is compared with the zero line, okay, zero line. So whenever the input is going to cross zero, the output is going to change its state. So when the output is going to change its state, it will be like a square wave waveform or the pulse waveform. So we can say that this input will be converted to an output like a square wave or the pulse. So the output will be looking like this. Okay, so it will going to change the state as the input is going to cross the zero line. So here option B will be the right answer, sine wave to square wave. You can say that this type of a comparator, which is a zero crossing detector, which is going to compare the zero line with the particular sine wave input, and the output will be a change of states waveform. It will be either plus Vsat or minus Vsat, and that will show you an output of a square wave. So it is option B, that is sine wave to square wave generator. So here for explanation, you can see, you can remember that in zero crossing detectors, the output waveform is always a square wave for the applied sinusoidal input signal. So here option B will be the right answer, sine wave to square wave generator. Then we'll go to question number 56. Dash is an op-amp based comparator for which a reference voltage is applied to its non-inverting terminal and the input voltage is applied to the inverting terminal. Okay, so if the reference voltage, that is Vref, is applied to non-inverting, and when the actual input voltage is applied to the inverting terminal, then this type of comparator will be called as inverting comparator. Okay, so option A will be the right answer here, inverting comparator. So here if you see the explanation, an inverting comparator is an op-amp based comparator for which a reference voltage is applied to its non-inverting terminal and the input voltage is applied to its inverting. So here you can see the answer, that option A is the right answer, inverting comparator. Then we'll go to the next question, question number 57. A voltage follower. Okay, now a voltage follower is a circuit which you can see it like this. If you draw the voltage follower with op-amp based, so here you can see this is minus plus terminal. So here you can see minus plus terminal, and here you can see the output. So this inverting terminal is connected to the output, it is a feedback, and then the non-inverting terminal will be given a voltage. Okay, now whatever voltage V in you have here, the same voltage will be seen at the output. So V out is equal to V in, because the gain will be unity here, because you're just going to connect the inverting terminal to the output. So gain is unity. So gain is 1, it is unity, and it is a non-inverting combination, okay, and it has no feedback resistor. So all these first three options, if you see this option, and this option exist in the circuit. So here the right answer will be option D. Voltage follower has all of these points, that is, it has voltage gain of 1, it is a non-inverting combination, and it has no feedback resistor. So here option D is the right answer. It has all of the above mentioned features. Then we'll go to the next question, question number 58. The input applied to an inverting amplifier is what? Is how? Means options are equal to the output, equal to inverted output, not equal to output, or output is equal to input. So here, when the input is applied to the inverting terminal of an amplifier or inverting terminal of an op-amp, then the output will be equal to inverted output. Okay, so it will be inverted output. No doubt it will be amplified, but it will be an inverted output. So option B will be the right answer, equal to inverted output. So here, if you see the explanation here, the name itself indicates it is an inverting amplifier. So the input applied to is inverted and is given at the output. Suppose the input applied is sinusoidal, then the output will be like this. So here we have shown the inputs and outputs. So if this is the input applied, so here input applied, here you can see the output is inverted. So this plus half wave becomes minus half wave, and this minus half wave becomes plus half wave. So here you can see option B is the right answer, equal to inverted out. Then we'll go to the next question, question number 59. In an inverting amplifier circuit, the output voltage V0 is expressed as a function of what? Input current, output current, source voltage, or source current? Obviously, it is source voltage. It is the function of the input voltage, that is the source voltage. So option C will be the right answer, source voltage. So here, if you see the explanation, the goal of an inverting circuit is to express output voltage V0 as a function of source voltage Vs. So here option C, that is the source voltage, will be the right answer. Then we'll go to question number 60. The other name for gain is what? Okay, now whenever we have an op-amp, op-amp will be having the output as the difference of the two inputs and multiplied by gain factor. There will be a gain. If you speak about ideal op-amp, it is having infinite gain. So gain is how many times you're going to increase the difference of the two inputs at the output. So that gain is nothing but a scaling factor. You're scaling it, how many times you want the output more. So it is a scaling factor. So here, out of these four options, option A, that is a scaling factor, will be the right answer for gain. So the other name for gain is scaling factor. So here you can see the explanation. The gain is also known as scaling factor, and it is the ratio of feedback resistor upon the source resistor in case of an inverting amplifier. In non-inverting, you can see as 1 plus Rf upon Rs. So this is a scaling factor, that how many times you want the output more. Okay, so that depends upon the resistances what you connect in the feedback and the source of that particular amplifier circuit. Okay, so here the gain is also known as scaling factor. So the other name for gain is scaling factor. So option A will be the right answer here. Thank you, students.